the R square is the one of the key thing. So there, even if you get greater than 40% also, we will still consider the model to look at. It's a purely depends on what type of problem. If it is an operation problem, there, as I said, that the accuracy is the key thing, right? So there, even 80% also sometimes will be low, right? Mahesh, does that make sense? Okay, what other questions you have in mind?
Sir, OLS is a technique in linear regression.
Correct. OLS is an algorithm, right? Which I was mentioning that. An algorithm which I was referring that, minimize, I mean, you are using the optimization problem is minimize. The objective function is what? Sum of squares of error, right? So whichever values you are getting a minimum value for beta and constant, and that will be your best values of beta and constant. So since we are using sum of squares of error is the objective function or a cost function, so this is the technique this technique we called as a ordinary least square regression. Prarana, I think the gradient descent part I not yet covered. I'm going to discuss about in today's in towards end of the session. So as I said that the gradient descent is a one algorithm we use for solving your optimization problem. So the optimization problem is this one, and this is the place we are going to use the gradient descent algorithm. Or sometimes we also use SGDA, stochastic gradient descent algorithm. So we will discuss about towards end of the session. But at this point of time, I think in the last session I was explaining about a detailed steps of any kind of a predictive modeling project, and we also discussed a use case and how to solve that use case with the help of linear regression. I think that's the place we discussed with the automobile case study. That is your assumptions which we discussed. Yes, of course. If there are two things which I was referring that if linear regression versus any other techniques. The linear regression works when you have your y and x have some kind of a linear relationship. If y and x doesn't have linear relationship, either you will convert your x into some transformed variable and such a way that you will have a linear relationship. Otherwise, you will drop that variable, or otherwise you can also think about if any other technique can help to solve the problem. But as I said in the last session, if it is a regression, then that is the first thing you need to make sure that your y should be continuous. And if it is a linear regression, there are few assumptions we discussed. Y should follow normal, and y and x should have linear relationship, no outlier, no multicollinearity, no heteroscedasty, and no autocorrelation. So of course, autocorrelation, more related to time series kind of a data. But at this point of time, the autocorrelation may not be a bigger thing, but the other 4 or 5 things which I was mentioning, those things you need to really think about it. Okay, online guys, any more questions? Okay, so Mahesh is saying that why should we follow a normal in the case of linear regression? So I will discuss about the consequences of that. I think today, I think in the last session where we concluded, guys. So I think what did we do is we discussed about the data preparation 1 and data preparation 2, correct? So I think we completed this part. I think we are at to start the data preparation step 2. So I think probably today, while I'm explaining this one, I will also explain what is the reasons for that. Sure, Vishaka. Anyway, I'm going to talk about these things in a while. So while I'm explaining that, I can discuss about that. Okay, so let me quickly open the case study, and I think I already discussed about all of these things. Probably I will skip to explain again. So I think this is the place I stopped. We created a new file with the numeric variables and the categorical variables, and finally this is the place we stopped it. You remember the categorical variables you got it, and the numerical variables we cleaned the data, and now we combine, and the new data frame we called as a cost sales new. Any questions on this till now? No, right? Okay, so now let's understand the data preparation step 3, the assumptions of linear regressions. So the assumptions of linear regression is, one second. Okay, the assumption says basically, first assumption we are saying that y should follow normal distribution. Okay, so the reason we will come to know in a while, but for the time being, let's understand the process. Then we will discuss about why it required to follow normal. So I think that you will get to know probably when I'm explaining about the regression as a model. There we will discuss about the reason for why. But at this point of time, just think about what is a normal and how can we identify whether data is following a normal or not. So how we can do that? If y is following a normal or not, how will you check it? I think this is the place, what we discussed is, I think the normality, I think in the very beginning.
Still I have to search 3 points, right?
Suppose if data is following a normal distribution or not. If data is following normal or not. How we can do that? There are multiple ways you can do that. Okay, so there are multiple ways you can do, to check whether data is following the normal or not. How can we check it is, first thing is by looking at the histogram of the data. So if the data is following a, histogram, something like a bell-shaped curve. And the second thing is, it should be symmetric. And the third one is 65%, 68%, 95%, 99%. So what does this mean? Plus or minus 1 standard deviation, you have 68%, plus or minus 2 standard deviation, 95%, plus or minus 3 standard deviation, 99.7%. So that is the data which you can think about. Mean equal to median equal to mode. So this is another important characteristics of normal distribution. So I think by looking at the histogram, these things you can validate some extent. So this is how you can identify whether data is following a normal or not. There is another way to follow a normal or not using a statistical test. So some tests like Durbin-Watson test, Shapiro test. Yeah. So like this, there are a few statistical tests also can help you whether data is follows normal or not. Right. So I think, we don't need to look at this one, but I think if you look at the histogram, by looking at these characteristics, more or less, you can conclude that the data is following a close to normal or not. No, it is. I'm saying that these are the characteristics. So it is not as strict as what we are trying to do. You know, we always look at a near normal. Near normal means this follows these characteristics somewhat closer to normal or not. So that is what something. Okay, suppose if y is following normal, there is no issue. So if y is not following normal, what we will do? So y we will transform into, and then suppose if comes z and the z follows normal. Right, the y passing through some transformation in such a way that you will get the z will follow normal. So that means that z equal to some function of y. Okay, so basically indirectly what I'm saying is z is not following a normal. What does that mean? Sorry, y is not following a normal. Y follows some other distribution. Every data should follow some distribution, right? So that means y is not following a normal distribution. That means that it's following some other distribution. So basically what we are doing, we are applying some transformation such that you're converting some other distribution into normal distribution. Am I correct or not? A simple example is if the data is following exponential distribution. Y is following a exponential distribution. And what is your transformation? The transformation can be log. If the data is following a log normal distribution, then exponential can be a transformation. Or if the data is following a binomial, then that it has some kind of a transformation like logit or a probit, right? So like this, if the data follows a particular distribution, to convert that particular distribution into normal distribution, we'll apply some kind of a transformation. So indirectly what I'm saying is linear regression works on only the data follows a normal. If the data follows some other distribution, you are extending the concept of linear regression to every distribution by applying a transformation. So this concept we call it as a generalized linear models. So linear regression works for what? For the data for which is normal. Generalized linear models, what does it mean? It works with every type of distribution where you can convert y into a normal distribution, right? So to convert into normal distribution, we use some transformation. That transformation is nothing but some function, right? That transformation is, we call it as a link function. So if z equal to f of y is nothing but what? F is link function. F is link function. Are you clear now? Are you clear or not? So basically earlier what we are doing, we are restricting ourselves with y is normal. If y is not normal also still we are able to do. How? By applying a transformation. So once you convert into transformation and once you got the model, then you will revisit it. For example, suppose your y is not following a normal distribution. Y is following, for example, exponential distribution. Then what will you do? A log y will be your transformed variable, which is nothing but z. Okay, so now when we do building a model, log y equal to beta 1 x1 plus beta 2 x2 plus and so on, beta n xn plus constant. This is the kind of a model you will build. Now what is your y will be? Exponential of beta 1 x1 plus beta 2 x2 plus and so on, beta n xn plus constant. Are you able to follow me? So this is how generally we will apply reverse transformation once you build the model to get the actual value. Is this clear? So now you understand the concept of the general and linear models. Now what is the difference between linear models versus general and linear models? Online guys, any questions on this? Okay, cool. So now this is the exact thing which I'm trying to do. Okay, now you have the data of car sales. Now what we want to do is, okay, look at the data. This is something looks like this. Okay, now if I want to get the histogram of this one, how will you get it? So there are multiple ways you can get it. One is using a Seaborn, there is a distribution plot, you have it. Or in the pandas itself, there is a method called plot. There you can specify hist, option equal to hist. Or there is a hist is a method itself, you have it. So to check, the assumptions check, right? So in this case, what I have done that, okay, I have the data. Now I'm just using the hist is the function which can help me to get the histogram of the data of the series. The series is what? Sales in 1000. So is it following normal distribution? All right. So if it is not following a normal distribution, what we need to do? So transform into, or as I said, that this is another way of looking at. This is also, of course, the distribution plot is also same. Now what we are doing is we are applying a transformation called log, which is, because the distribution is more like exponential distribution. So in that kind of scenario, if you apply a log transformation, so log of this variable, okay, and finally you will get a log sales in 1000, right? So the log sales in 1000 is nothing but what? Log of sales in thousands. And okay, now here I just added a +1. What is this means? Why I'm doing that? Yeah, it is not constant. Basically, suppose if log is works solely on positive values. Suppose log 0. Can you define log 0? You cannot define. So that kind of situation, if sales sometimes is 0, that means you will get an infinity value or something. So that's the reason, to avoid that one, you're adding a 1 to everything so that you will get appropriate values. So that's the reason just I used it. So whenever you're applying some kind of a log transformation, etc., it's always good to use the +1. Okay, anyway, it doesn't matter, there is no change, because at the end of the day, the transformation you are doing it. No, the data looks like exponential data, right? It's because the data is, suppose, if you remember the distributions which I was showing, that the exponentially is something like this, or exponentially is something like this. Both are, this is a negative thing and this is a positive thing. So in both the cases, the log can work. It's a positive skewed or a negative skewed kind of scenario. Both the situations, you will get the values.
Chandra, can you please explain that log transformation?
Graph for this one, which we have changed now, transformed.
That is I'm trying to do now. So now I created a new variable called log sales in 1000. Okay. Now if I look at the log sales in 1000 for the new data, now can you check it now? Is it somewhat similar to, of course, not 100% 100% to normal, but it's a close to normal. So Rajesh, what is your question? Because what I'm saying is, since my data is not following a normal distribution, if based on the data, you need to apply some kind of a transformations. The very common transformation is if the data is in a skewed distribution, either it's positive skewed or negative skewed, and that's the kind of situation, the log can be one of the appropriate transformation.
Our intention is to connect to our
since my data is not log, not following a normal distribution, it's a more skewed distribution. then what I have done is I used applying a log transformation, and now after applying a log transformation, you can see my transformed variable how the distribution looks like.
Okay. Thank
Right?
you. Yeah.
So I think this is much better than the earlier one, right? In terms of the normality perspective, right? So that's how you will cross check yourself whether the new variable follows a normal or not. Suppose some reason if this is also not following a normal, that means still you cannot use the linear regression in this case. So of course, see, even if you apply linear regression, some results you will get it, but the results may not be 100% rely on. Is this clear?
So I have a
So
question.
now you understand the assumption of a linearity, sorry, normality to check. Okay. Once you are fine with the new variable, now what is your new variable? Log of sales in 1000 is your new variable, right? Not the sales in 1000, because now your dependent variable is log sales in 1000. So for that, what I have done is I drop the sales in 1000 variable from the data. Okay, correct or not? So once I have the list of variables, now you got it. These are my list of variables, and after exclusion of my sales in 1000. So now my new dependent variable will be log sales in 1000, and these are my list of X variables. Once we have this one, now the second criteria is what?
Other like correlation and
Okay, the second assumption. What is the assumption? Second assumption?
other
Linearity assumption. What is your linearity assumption?
log of y and under x.
Yes, your y and x should have some linear relationship. So when I say linear relationship, what does that mean? Linear relationship. Okay, so when can you say that two variables have a linear relationship? One increasing and other one is increasing, or one increasing and other one decreasing. In both the cases, we can say that the data is following a linear relationship. So this is same as the definition of correlation. What is the correlation? The correlation is a linear relationship between two numerical variables. Yes or no? If variable between two variables you have a correlation is high, then you can say that there is a strong linear relationship. If the correlation is close to zero, what does that mean? There is no linear relationship. That doesn't mean that there is no relationship. So you may have some kind of a non-linear relationship, but correlation coefficient will not capture the non-linear relationship between two variables. Correlation coefficient always tells me that a linear relationship. Okay, so in this case, what we need to do is to check correlation between, to check linear relationship between your y and x. How can we check it? You should have your y and you should have your x1, x2 and x3, x4, etc. And now you look at calculate the correlation. So for example, you got 0.1, 0.2, 0.35, 0.45, 0.55, something like that, you got it. So what does that mean? Some variables are not having a strong linear relationship, some variables are having a So in this case, the typical cutoff we take is 0.1 and above. At least some relationship you should have, some linear relationship you do. If it is less than 0.1, what does that mean? Is that it's almost close to zero, that there is no linear relationship. Okay, so that is one kind of a thing which we do that. Even if we do 0.2, 0.2 may not be a very significant linear relationship. Okay, so in case that kind of situations, what generally we do is, okay, look at your y and you look at your, look at your x1 and take some transformations of x1, log x1, exponential of x1, square of x1 square root of x1. Am I right or wrong? So now what I can do, okay, this is giving me a 0.2 or 0.1, this is giving me a 0.3, this is giving me a 0.2, this is giving me a 0.15, this is giving me a 0.4. Which one is having a high correlation with your y? Square root of x1. So that kind of situation, instead of using x1, if I use square root of x1, and that will give you highest strong linear relationship. So that's how you will also apply transformations on x1 or x variables such that which transformations gives me highest correlations with your y. Of course, each variable you need to do that. Otherwise, how will you understand that?
And Chandra,
So this is the place. Of course, you can think about some user-defined functions. Okay, using a user-defined function, how to capture that information. So, for example, if I want to look at a quickly relationship between your y and x, how will you do that? So the correlation coefficient, and of course, correlation coefficient. In case if you want to see that, you can see that. So this is the correlation metric you got, right or wrong? So this is a correlation between what? Every variables. Now what I'm saying is, what is my y variable in this case? Okay. So sales in 1000 is your y variable, right? So now what we can do is, you can think about which of the variables are having a very less linear relationship. Do you think these variables are having a very less relationship with your y? Correct. If you look at this one, this is almost less than 0.1. So obviously, by default, by looking at this, you can easily right. So that is what I'm trying to do right now. Am I correct or not? So this is how you can identify your correlation between your y and x. So if sometimes, suppose some of the variables are having a less linear relationship, either you can drop or look at each variable and which transformations can give you the best linear relationship with your y. In case that is an option of method one, suppose if the y and x having a very less linear relationship. So okay, y and x have very less linear relationship. So what we will do that? What we will do that?
Will transform using
First thing is method one. Option, step one. Either you may drop those variables. You may drop those x variables. This is method one. The method two is, okay, look at the transformations of x and identify the best transformation of x such that gives significant correlations with your y. Okay, now tell me, if I want to define a user-defined function over here, for example, some variables are having a very less linear relationship. So what shall we do that?
transform.
So either you can drop them or you can look at them. So what generally we do is we look at the, okay, define a linear relationship of x. For a given x, what we will do? What we will do?
Check if less than 0.1 0.1.
Okay, so no, that is first thing. Whether checking is even if a variable having a higher relationship also still always good to check. If any other transformation gives you a highest correlation. Even for example, some variable you got it as a 0.4. Even still, x is giving a 0.4, but log x is giving a 0.5, for example, or maybe exponential of x is giving a 0.6. So then probably still I will prefer to go with the exponential, because the exponential will have a strong linear relationship with your y. So first calculate different variables. Okay, how will you do that? How can we do that? So apply some kind of transformations. What is the transformation? Okay, a log x equal to np dot log of x plus 1. I'm just keeping as a, and what is the other one? Exponential of x equal to np dot exponential of x and square of x, or square root of x, and np dot square root of x, and what is that? Square of x. So in this case probably x multiplied with x, right? Now what we need to do? Correlation matrix. Okay, how will you do that correlation matrix? How will you do that? Okay, if I want to perform a correlations, how will you do that? Okay, so you will try to calculate all the correlations there. Okay, so maybe what you can do is you can think about correlation with x. Okay, now what we will do here? Okay, so let's do one thing. Let's do outside of this one. So for example, you have your y variable is what? Car sales new dot, and for example your y variable is log sales in thousands. Okay, and comma, and car sales new dot, maybe example, let's take an engine size. And if I want to take correlation between these two, how will you do that? np dot core okay, so if I do this one, what we will get it? This one, right? So probably in this case the value is coming as a 2,2. Sorry. How will you extract a particular value? This is index is 2. because this is giving a metric, right? So now, okay, it's area of the metric. Okay, in this case, the first thing is what you want to take. You want to take a, okay, in this you want to take the first value. Still you're not doing. Yeah, so this is the value of correlation coefficient, right? Correct or not? So now I want to get this kind of a correlation coefficients for everything. Then you can apply this transformation on the every variable on your data. Will you able to do that or not? So how can we do that? Okay, correlation coefficient for log x. How will you do that?
Chandra, I have a doubt.
So you can specify your x comma y, and then what you can do is np dot log of x plus 1, and this is the place you can say that and of course what you can do, you can pick up this information. This is a correlation for log x. This is a correlation for so okay, once we do that, return. What we need to return? List, right? So either list you can do, or even series also you can do. What is dot? PD dot, and of course you can specify what are the variables you want to drop it. So this is the one thing you want to use it, and this is the one thing you want to use it. Okay, so if this is you want to apply on your y variable, now what you can do is, okay, so the linear relationships I need to look at between what your sales in 1000 is your x variable, this is my x, and this is my y, correct? What happened? Invalid scalar variable. Is there? Sorry. Okay. But this is not the one. Oh, okay. So y comma, yeah, sorry, I think you are correct. Yeah, so now you got the values for each individual correlation coefficient, right? Of course, in case if you want to give the index maybe what you can do, you can also try with the correlation with X also, you can include it. So NP dot, because I want to see that Y comma X, correct? So if I want to include, I can include this one. Now if I want to apply this one on the, okay, sorry, this is also I need to include. And I want to give the index to this one. How will you give the index? Index equal to, I can give the list of name. Correlation X, correlation with log X, correlation with the exponential X, correlation with square root of X, and the correlation with square of X. Okay. So now in this case, you can see that the exponential is giving a high, it's a 0.13. So probably I can choose this one.
Yeah, Chandra, hello.
I can choose this one. So that's how you can take it, whatever the value it is.
Chandra,
Because the correlation with the exponential of X is giving you high correlation. That is what we need to consider. Minus or plus, it's a, even correlation coefficient can be a positive or correlation coefficient can be negative. You know, if the value is close to 0, it is not having a linear relationship. If it is a close to -1, it's very strong negative linear relationship. If it is a close to +1, then it's a positive linear relationship. Okay, now if I want to apply this relationship on all the variables in my data, how will you do that? Car sales. So new and apply on what we need to do. You need to apply the function, right? And of course, this is the function. You can think about it. Now, if you apply this one, what happened? Okay, so I need to supply. I have to supply y, right? What is your y variable? So the linear relationship with y. What is your y? Okay, so x sure. Your x is anything, right? One second. Lambda of x and so now you can see that each variable wise, what is the correlation coefficient? Correct. Now you can easily look at, okay, these are my correlation coefficient, and now this you can export it, right? So what you can export is basically you can think about, okay, this is my correlation relationship, a linear relationship with your y. Okay, so now once you have this one, what you can do is to CSV and the linear relationships. Okay, now if you see that this is my data you got. Now, of course, this is what you got it. Now you can easily look at each variable wise which one is having a strong relation. Of course, this array you got it right. Probably you can convert this array into a single value. How will you do that? This is, you got the array right, array of this value. How can we convert this value into a normal value? How can we do that? So probably what you can do is, okay, what is that series? The series is basically pd dot yeah. So this is what you got it. Now if I look at the index also you got it. Define. Just I'm simplifying this, guys. Don't worry about that. So you will not get that list. That is the thing which I'm trying to locate for you. These are all are some playing around with the indexes, nothing else. So now you got this one. Of course, I think probably I did not add the square root part. Okay, but you got the values of this one. Now you can easily say that, okay, my 4-year resale value, if I take as it is 0.43, which one is the best one? Log x gives you a better relationship. And in this case, log x giving you a better relationship. So this is how you can identify which relationship is best for a given x variable.
Chandra, hello.
This will be a super helpful when you are trying to improve the accuracy. I mean, this is what we call as the linear relationships.
Chandra, are you able to
follow
hear
me or not?
Chandra, I have a doubt, Chandra.
Yes sir, now what we are doing here? We are not doing anything. We are trying to identify a best linear relationship, because that is the assumption which I was referring that. Okay, I think someone have questions. Rajesh, do you have any questions?
Hi, Chandra,
I'm not able to hear you.
Are you able to hear me now? Hello, Chandra? Hello? Hello, Chandra? Hello?
1 second, looks like. Yeah, can you speak now?
Am I audible?
Yes, am I audible? Yeah.
Chandra, I've been trying to speak out for a pretty long time.
Yeah, I think, somehow my voice is mute, so it's fine. Yeah, now you can talk.
Please, I want you to explain from line number 96. If I'm, please correct me if I'm wrong. First thing is that y, the value of y that we got was an exponential. We converted that particular y value to a normal distribution. Who's that? We were checking for the best correlation between x and y, and the steps that is mentioned in 97 is for that, right? Correlation of, we checked with log of x, exponential, square, and square root, right?
Correct, exactly.
And post that, how did we mention like the value of 0.13 is in best correlation with y? That is my question. How did we come to that particular conclusion?
No, I'm saying that look at all possible things. So for example, here, if you look at this one, and if you look at this one, which one is highest value out of all of these things? So I'm talking about absolute value. Absolute value, the exponential is giving them 0.13, the remaining are 0.10 or 0.11, right?
Yeah, Chandra.
So this is what exactly, if the correlation value is high, you can say that more a linear relationship is existed.
Oh, okay, fine. Yeah.
That's the reason I was explaining the correlation coefficient concept.
Oh.
If the correlation coefficient is high, then you have a more stronger linear relationship.
Okay, fine. So we will make an relationship between the log of 5 that we have concluded and correlation of exponential of x, right?
Yes. So what I'm saying is the correlation of, the exponential of x is giving you high correlation with your y compared to any other transformation.
Correct.
So now here y is my log sales in thousands.
Correct, Chandra. Yeah.
Okay. So if I look at this one, what are my best relationship you can identify? So now if you can see that, what are my variables which you can think about it? And in this case, which one is best? You can say that this is my best relationship in this case, this is my best relationship. For this also you are getting this is the best relationship. And what about this one? Even in this case also, this is the best is giving you. And out of this one, if you look at, this is giving you the best, it's giving you. And in this case, none of them is giving best. Of course, if you want to see that, this is a little relatively better because it's a 0.1 and above, you can consider. In this case, which one is giving a better linear relationship? Maybe 20.7. As it is variable only giving you a best relationship. And cob weight, of course, none of them is giving more than 1.1, and even in this case also none of them giving more than 0.1. In this case, again, if you look at the log is giving you a better relationship. Even in this case also, the log is giving you a better relationship. Correct or not? And even in this case, which one is giving a better relationship? I think the log only is giving you a better relationship. And in this case, none of them is giving better. And even the same thing with here, and same thing in this here also. And same, of course, here, this is giving you a little better. Then in this case, if you see that normal variable is giving 0.1 and this variable is giving, and what about manufactured Ford? You can see that this one is giving a better relationship, correct? Even in this case also, this is giving a better relationship. Yes or no?
Yes, Chandra. Yeah, correct. Okay.
So even this one you can drop, and this one you can drop, this one you can drop. Even in this case, this is normal variable. I mean, probably this variable is giving you a better relationship. And in this case, normal variable itself, or maybe this variable is giving a better relationship. And this you can drop it. And in this case, you can see that this is giving you a better relationship. Correct?
Correct, Chandra. Okay.
So even you can drop this variable, you can drop this, I mean, probably if you want to include, you can include as it is variable, or maybe this one. Or in this case, you can see that this is giving a better. So this is how you can identify a best transformation out of it. Otherwise, if none of them is giving, probably you can exclude that variable, because that variable anyway, you are not getting any linear relationship. So at least my target is 0.1 and above, which transformation is give you and which one is the highest. So that can be, you can consider. Yes, of course, you can try all possible logic, in your programming. That is the place you're programming, the concept of all the things what you learn, that will be helpful for you.
Chandra, this is Uttam.
Yes, Uttam.
I have sent you an email. Maybe we can discuss this tomorrow after you read the email. It's a website that discusses the normality assumption. And it says that the linear regression doesn't require the normality of the Y as much as it requires the normality of the errors that you get. So maybe after you read what I've sent, we can discuss it again tomorrow. I want a clarification of which one is right, which one is wrong.
Okay. So you are correct, that I will talk about. That's the reason I did not discuss about at this point of time what is the reason for that. But you are partially correct on that. We will discuss. We'll have a conversation around that. So now you understand how to choose the variables and how to drop the variables by looking at the linear relationships.
So Chandra, one question, Prerna this side. So
yeah,
you are choosing within the dummy variables also. So do we need to go to that extent? I mean, so so many manufacturers, right? So will we go ahead and in our practice, we'll choose from within those category dummy variables as well?
Yes. So ideally you are correct. So for a dummy variables, we may not really look at that level of transformations and etc. But yes, if you are really looking for some accuracy improvement, probably you can also try even the transformation on that also.
Okay. Okay. Sure. Thank you.
Yeah. So, but yes, if you are looking for a quick wins, so you don't need to really look at the dummy variables. You can simply look at these are the list of variables which you want to include best transformation. The dummy variables you can use as it is, because you don't see a significant improvement in the dummy variables. You see that all of the variables are more or less maybe a 0.1, 0.01 something difference. You can see that, but more or less all of them are a similar kind of a it won't see a lot of improvement basically. But yes, one or two variables probably might have improvement, but mostly the dummy variables will not see a significant improvement if you even apply the transformation on them. Does that make sense? Now, if I want to include Fourier resale value, instead of that, what you can include? Log of Fourier resale value. Does that make sense? So I think the when I was referring here, what I'm referring is which of the variables are important, which of the variables are not important. That is the first thing you will get to know. So what relationship do you notice? That is something, what are the things you need to look at? One is which variables are having a relationship with your y. When I say relationship, means linear relationship. This is the first thing you will understand. The second one is which transformation gives you high correlation with your, which transformation on x gives you high correlation with your y. Okay, so based on this, based on the above, you will choose variables with correlations greater than 0.1 and variables with high, transformed variables with high correlation. So this is your final thing which you will choose it. Are you able to follow me or not? Any questions on this? You're clear? So this is what exactly we will do that days. So now you understand the normality part and the linearity part. Any questions on that? Okay, cool. If we don't have that one, probably we can move forward with the next step. Of course, we already removed the, what did we remove? What did we remove? We already removed the outlier spot. So the fourth part, which is nothing but multicollinearity part. So the multicollinearity part I will discuss about in a while. But at this point of time, if you think about the first two assumptions are, which are very important assumptions. Okay, so now once I have the data, now what is the next thing I need to do? Split the data into train and test. How will you split the data into train and test? Okay, this is the place, a train test split you have option. So here is the place we have two types of splitting we do that. So let me explain that. So suppose you have a data like you have a customer data, for example, customer ID, and your X1, X2, X3, X4, and you have Y, and like you have a 10 data set. Okay, so then probably some values you got it. This is your Y variable. These are my X variables. Assuming that you want to split the data into train and test with 70% and 30%. Okay. Now, this is what my target variable. These are my what? My feature variables. Feature variables. Okay, so my target and feature variables, you have it. Now, when I'm splitting the data, so there are two ways of splitting the data. One is your train Y and the test Y, and the train X and test X. Okay, this is a one type of splitting. So you are splitting your Y and X separately. And the other one is both X and Y will be there, but you are splitting the data into train and test. Okay, so here you will have a data of both X and Y in a single data frame. Does that make sense? So now the thing is, for example, you are randomly splitting the 70-30. That means 30% is, for example, this is my 30%. So randomly you got three values. So these are my test data. The yellow one is assuming that the test data. Now the 70% is train data. So now what is your train data? Your train data will be Correct or not? This is my train data. And what is your test data? So in this case, this is my first. Correct or not? So this is my train and test. But if I want to get a train X separately, train Y separately, how will you do that? So train X. So what is your train X? This is my train X. And the test X, this is my test X. And what is your train Y? So of course, this one. And the test Y. So you are clear now what is train test split, how it is done. So the train and test, sometimes what happens is some functions need arguments as a X and Y separately. Some functions you need arguments as in single data frame you can substitute. Like for example, stat models, it will take both a tray X and Y separately as well as and Y and X in a single data frame also you can take it. But whereas a scikit-learn, it always required Y separately, X separately. Are you clear? So now why I am talking about. So in both the cases, suppose if I want to split into 4 data things, so you can use a train test split is the function which is available under scikit-learn cross-validation module. And if you want to split the data, what you will do is you will directly split what is the data set you have it. Suppose your data set is car sales new and comma your test size is for example 0.3, and then to come up with the sample you will provide some kind of a seed, like a random seed. Say maybe you can give a 1 2 3 or something. What is this mean is the same sample, if you want to repeat again, you will use the same seed for a same data set. Okay, that is nothing but test size means you are splitting the data into train and test, right? So 0.3 is nothing but 30%. So remaining train data is 70%. So in this case, you will get the train data and the test data as a 2 data sets. You will get it as an output if I use this function. But if I use a different function, so train X and train Y, test X, test Y. So this will give me a 4 data frame. If you provide, okay, my car sales new, your Y variable, okay, comma, car sales all X variables. Suppose if you supply your Y variable separately, your X variable as a metric separately, then you will get the train X, train Y, test X, test Y. Sorry, first if you provide X, then you will get the X variables first. If you provide Y, you will get the Y variable. So in this case, if you are specifying train X, that means you should have first X. And if you are looking for a Y, then you will get the Y separately, second Y. The seed is something what I was referring is, okay, seed I will talk about. Now are you clear on the functions? What is the functions means? Guys online, guys, any questions on this? How a train and test data will get splitted using a scikit-learn?
Would that 30% of data selected randomly or what?
Yes, it's a simple random sample.
Okay.
Okay, so what I was referring is the seed is something will help you to create a standard normal uniform distribution. So for example, when I was referring that I need to take these three observations, you cannot take randomly three observations unless it's equally proportional distribution. So what I mean to say that, suppose you have a data. So what this will do is it will split the data into between 0 and 1. So you will get some kind of a uniform distribution. What is uniform distribution will do is, yeah. So when you are doing this one random, what is this random distribution will do is, it will create a value between 0 and 1 in such a way that if I take less than 0.1, you will have 10% of observations. If I take 0.1 and 0.2, you will have another 10% of observations. So uniform distribution is nothing but what? If I take equal intervals, you will have an equal proportion of observations. Are you able to follow me? So what I'm saying is, it will create some kind of a distributed variable, and that distributed variable is basically will do is between 0 and 1, if you take any equal interval, so equal intervals means like for example 0 to 0.1, that is nothing but what? 10%. So if you look at if I have 100 observations, 10 observations you will have within that, between those two values. Are you clear? So whenever you want to select 30%, what you can do randomly? You can take less than 0.3, then that will give you 30% observations, because it's a 0 to 0.3 is nothing but 30%. So 30% means the 30% of observations will be assigned to that, the value is less than 0.3. So to define this uniform distribution, you should need some kind of a seed. For a given seed, the distribution will be the same. So if I don't supply the seed, what happened? It will take a system time as a seed for defining the uniform distribution. So indirectly what I'm saying is, okay, if I'm taking randomly 30%, what does that mean? You can take any three observation as a 30%, right? If I don't supply the seed, even tomorrow if I run the code, I may get any of these three observations. But if I supply the same seed on the same data, I will always get the same observations as part of my sample. So that tomorrow when you are running, you will not get slight different results. You will get the exact results. You can take any value for the seed. Only thing is, whenever you want to repeat the same sample, you need to use the same seed. Suppose tomorrow, if I give today is I've given 1, 2, 3, tomorrow I give 1, 2, 4, you may get a different sample because the seed is changed. So that is the difference between the seed. I mean, when I say seed is nothing but that one. So even in this case, what I'm doing is, I'm taking a feature columns. What do you mean feature columns? That's nothing but X variables. How can we get the X variables? My total data, you are differentiating with sales in thousands and log sales in thousand. Of course, sales in thousand, anyway, we removed it. There is no issue. I'm just removing the log sales in thousand. And that list we called as a X variables. Correct or not? These are my list of X variables after excluding this one. And if I want to use that train X, test X, train Y, test Y, first you need to specify list of X variables and then Y variable, and you specify test size equal to 0.3 and a random state, that is nothing but the seed, which is nothing but you given that. So in this case, what you are going to get it? You will get the 4 data sets because you supplied as an input as a X and Y separately. So even you remember, I given that in the second case, I given that X variables and Y variables separately. If I give a X variable separately and Y variable separately, I will get the train and test for X as well as Y. So that is what exactly you are looking at. Suppose if you look at my total number of observations, in my total number of observations, how many observations are there? Around 157 observations are there. If you look at my train and test, how much? 109 and 48. So 157 observations, 30% means what? Approximately 48. So that is what you got it.
Chandra, over here for code line number 106, for the train test split, car sales new feature columns. Should you consider all the other values that you have mentioned above?
Yes, all the X variables in your data. The feature columns, I extracted feature columns from here, right? The column names.
Okay. So for those columns that are having less correlation, are we not dropping it?
Of course, at this point of time, I did not drop it, but yes, ideally you should drop it.
Okay, and sorry to if I'm wrong, but then few of the rows were having high correlation with correlation of log of x, and some of them were having high correlation with correlation of exponential of x. So random columns would be rows would be selected. How is it?
No. See, first of all, what you need to do is,
Yeah.
after this one,
Yeah.
what you need to include is, you need to include what are the variables which are high correlated with your y.
Correct.
So first, that is the first thing. And second thing is with your exponential. Then what you need to do, you drop x variable and just create a exponential of that variable. A simple example is, in our case, what happened is, if you look at this one, the 4-year resale value. So what I want to do is 4-year resale value. I'm taking a log transformation, gives me a best transformation, right? So car sales new, within that a log of, this is my variable. Now take what we need to take. You take a log of np.log. Okay, and car sales so this is what I'm doing, and once I have done this one, I will drop what? I will drop my car sales new. So how will you drop it? Okay, car sales new and drop. And what is the list of columns you want to drop it? 4-year resale value.
Okay.
And access equal to 1, and of course in place equal to
True.
Of course, what you can do is first create all the variables which are highest linear relationship with that, and you can drop all the one in one go. You can drop all the variables. So
for my wheelbase, I will be selecting correlation of exponential of x, right?
For a wheelbase, yes, exponential of x, correct, exactly.
Great. Okay.
And for example, this variable, you can directly drop it. You don't need to create any new variable for that. Even these two also, you can drop it directly. And for this, you don't need to create any transformation. For example, length, you don't need to create any transformation because as it is variable is giving high linear relationship. Is that clear?
Yes, very clear. Thank you.
Okay, so that's how, of course, see these steps generally we do towards the end of the, after first iteration of the thing, but generally if you do take care of in the beginning itself, you get a model with a high accuracy in the beginning itself. Okay, so now you are clear with, the splitting the data into train and test with the train X and test X, train Y and test Y. But some reason if you want to create a train and test in this manner. So what? Train, test. So in this case, what you can do, directly you can supply the data set and you can use as it is these two things. There is no difference. Sorry. Right? Suppose now again you can look at that, the same set of variables you got. Same set of observations you got it, like 109 and 48. Of course, so I said that this will be used if you are applying scikit-learn as a package. This can be used when you are using stat models as a package. Are you clear? So in some scenarios, you can directly split the data into train and test. In some scenarios, you can split the data into train X, test X, train Y, test Y. So this is you use sklearn. I'm saying that when you are building a model using a stats models, there you need a train and test. You can directly give it with X and Y. Are you able to follow me? But for splitting the data, you are using a scikit-learn only. I'm talking about when you're building a model. When you're building a model, you need to give a train X, test X separately, or train X and train Y separately for scikit-learn functions. If you want to build a model using a stat models, you can use directly train with the Y and X in a single data frame. Okay, anyway, you will see that part in a while. Okay, so till now, any questions on this? I think now you're clear with the understanding of all of these things, right? Okay, now you need to build the model. Before building a model, you want to take a quick break. Okay, so let's take a quick break. It's 11:31, 11:45 we should be. Sorry?
106 and 109.
Okay, guys. So let's do one thing. 11:32 by 11:45 we should be here. So building a model, as I said that there are two packages or two modules can be helpful. One is a stat models, one is a scikit-learn. So both will give you the same results. Only thing is, stat models is the look and feel of output is a little better. So that is the one reason we prefer to use stat models for linear regression. But otherwise, there is no difference in terms of the results. Okay. So now let's understand in the stat models is the module. So what is the module we have? Stat module. Under that, we have a formula API. So there is a formula API is the submodule. This is the module will have all generalized linear models you can build out of it. So, okay. So what you can do is import as suppose some name you can give it. Now SMF dot. So then you have a different methods we have. So one of the method is OLS. Suppose if I use OLS, what you need to give it? You need to give the formula. Formula means y tilde sign x1 plus x2 plus and so on xn. Of course, constant you don't need to give it, automatically it will take it. So the data equal to train, and this is the only information in itself. And this is, you can save it as a some kind of like, okay, model 1. And now model 1 dot fit. This is your fitting the model. This is the, initializing the your y and x, and now you are building the model. Once you build the model, if you want to see the output, the model 1 dot summary is the output. You can see that. And once you have this model 1 output, suppose if you want to use this model 1, suppose you want to predict something, suppose predict train. So that means for the train data, you want to calculate the predicted value. You can use a predict function. So this is nothing but what? Your predicted value. Train predicted. Okay. And similarly, test predicted. Model 1 dot test predict. Sorry, predict. Are you able to follow me? So basically, if you understand this one, good thing is in Python, the steps are remain same. So even if you are using SMF.OLS, instead of OLS, if you are applying some other model like Logit, or if you are using a Logit, the process is as it is same. There is no difference. What is changing? Only the method will change, by providing a Y and X, the train data, fit the model, and identify. You will look at the summary, look at the predicting the values for train data, predicting the values for test data. The steps will be remain same. Are you able to follow me? So that is what exactly I'm looking at over here. So when I'm building the model, so what I'm doing in this case is, for example, as I said that, of course I have, right, of course here I don't need because I already imported the data. So the stat models formula API I'm calling as SMF. And now if I'm looking at SMF dot, you can see that there are different models you have it. So you remember I was referring that GLM, generalized linear models, or if you want to build a logistic regression, or if I want to build a OLS, Poisson, Probit, like this, there are different models we have it. Okay, so now what we are using is, we are using a OLS. And here what you need to supply is formula equal to, when I say formula, what is your Y and what is your X? So constant you need to give it, and then data equal to train, and that's all. Very clear now? So this is what exactly I'm trying to do over here. For example, smf.ols, and suppose this is my Y. Formula is basically what? Y tilde sign. Okay, x1 plus x2 plus x3 plus x4 plus etc. Suppose you have a different variables, and then you can just supply data equal to train. And of course, if you want to fit your directly here itself, you can do that. Otherwise, what you can do is you can just assign this one. And what is the name you given for that? I given that LM. So next, what you need to do, LM dot fit. Once you do the LM dot fit, that means the model is built. Now, once you do that, you want to see the summary of this one. Okay, 1 second. Now, what you need to do is, once you created the lm.fit, now you need to supply, you want to print that output of this LM model. So if you print this output, maybe you can see here what is my output looks like. Okay, so if you understand, I think the last week I explained about one small case. There, what I did is I explained in the Excel. You remember or not? In the Excel, I shown you output. I think the outputs also I have it in my Excel. So you guys remember linear regression in Excel? I created this one and I performed this regression, etc. Correct or not? So of course you can see that the calculation of R square and all of these things we calculated here. So in this case, there are 2-3 things which I was explaining over there. So let me explain the output of here. So the first thing is, if you look at the output, what is my output of my model should be? Output of my model should be what? What you should have it whenever I'm looking at the model output, what I'm expecting. Okay, the first thing is what you need to have it is, your hypothetical relationship is what? Y equal to beta 1 x1 plus beta 2 x2 plus beta 3 and x3 plus and so on beta n xn plus constant. So first of all, in our case, what is our model? Log sales in thousands equal to, I should have beta 1 times of price in sales in 1000 plus beta 2 times of, what are the variables I used? Price in 1000, 4-year resale value plus and so on plus and beta n times of last variable is what? Vehicle type passenger, right? So beta n into plus constant, correct? This is what we created the equation. Now what is your beta 1, beta 2? So first of all, my model should give me what is the beta 2, beta 3, beta 4, etc., beta n and constant. So these things we called as a estimates or a parameters or coefficients or betas or gradients. So these are different names. Okay, so these are all things what we're calling as a different names. So of course, in this case, the estimate is something which we should have it, right? That is the first thing. So my model output should have a estimates and corresponding values. And the second important thing which I should have it, the first thing is estimates. The second thing is how good is your model? How will you know how good is your model? So this is the place I told you R square is the metric, correct? And the third one is which variables are important. How will you know which variables are important? So you remember my beta value is high and your the impact of that variable is high. Suppose if you remember in the last in this case when we are taking the sales in thousands and the variable is marketing spend, I think that's what I explained, right? So what is this equation will be? You remember the equation? The equation is what we got it, y equal to 0.048 times of marketing spend plus constant. The constant is 4.3 or something, okay, for the time being just. And what is sales? This is y is the sales in thousands, correct? So this is what you got it. Now what is this means? What is this beta? In this case beta value is what? 0.048 and C is nothing but 4.3. So you remember the interpretation of the beta. If I change 1 unit of my marketing spend, what is the change in sales? Suppose if I increase 1 rupee in my marketing spend, how much increase in the sales? 4,000. So 480 or 48. Because if I multiply it with 0.048 into 1,000, that is nothing but what? 48. So that means that if I increase the spend of marketing spend by 1 rupee, there is a change of 48 rupees in sales. This is what the interpretation of this one. Suppose instead of 0.048, if you got 0.78, what does that mean? If I increase marketing spend by 1 rupee, I will get 78 rupees. So that means if my beta is high, can I say that the impact is high? Correct? If beta is close to 0, what does that mean? The impact is almost 0. Is that clear or not? So of course, if the data in thousands, this is what you got it. If data is as it is rupees, suppose sales equal to, then what is your equation will be? 48 times of marketing spend plus 430 rupees is as this, because of 4.3 into 1000. Right, sorry, 4030, right? 4300, sorry. Correct or not? 4.3 is multiplied with 1000. It's nothing but 4300. Yes or no? So this is your equation will be. So what I'm saying is, by looking at the absolute values of beta and constant, can you identify that these are close to 0 or not close to 0? You cannot really say that, because if based on the scale of the data, you may also have the betas are zeros or decimals or etc. So by looking at the absolute value of beta, I cannot really say that it's a close to zero or not, because if I have the data in thousands, this is what I got it. If the data is in as it is rupees, I got this one. So can I say that here my beta is high and here my beta is low? No, right? So that means by looking at the absolute value of beta, can I say that is this is close to zero? Is this not close to zero? No, right? So this is the place what generally we do is we use a hypothesis testing. What is the hypothesis testing? My null hypothesis is beta equal to 0. My alternate hypothesis is beta is different from 0. So beta equal to 0 means what? Beta equal to 0 means what? There is no effect of my x on y. If there is no effect of x on y, what is the use of that variable? It will not impact, right? That means that variable is insignificant. So that means that if I want to consider, if I want to conclude my variable is some impact on y, what we should do? We need to reject your null hypothesis. So that means that we need to reject null hypothesis. So that means that if I want to reject null hypothesis, what is your p-value should be? My p-value should be 0.05. I mean, my p-value is low, and you can reject your null hypothesis. So if it's p less than 0.05, can I say that at 95% level the variable is significant? Yes or no? So that is what exactly we are going to check, whether the variable is important or not. When I say variable is important, that means that variable is significant or not. When it's a significant or not, what does that mean? Is there any impact of x on y? Is there any impact of x on y? So that is nothing but what? Indirectly, we need to look at is beta is close to 0 or beta is different from 0. That's what we need to check it. So that is the hypothesis testing which we are going to do. So basically, the first thing is estimates. By looking at the estimates and the corresponding, the value of p, and you can easily identify where the variable is significant or not. And the third one is, of course, this is, you can say second one, this is a third one. And how good is your model? And one more important thing is, before doing this one, I also want to make sure that, suppose if all betas are close to 0, if all betas are close to 0, that means that none of the variable is coming significant. What does that mean?
Constant.
That is same as y equal to constant. That means that can you see any improvement in your model? So that means that is there any improvement in your x variable is improving your y? No. So in that case, can you say that there is no model is not possible? That is, you can say that, right? Because if all the variables are insignificant, that means that there is no model, right? So that is what we are going to check it. So in this case, the second point, if you look at whether model is possible or not. How can we check it? If all betas are close to 0. That means that if you look at my initial understanding of the the concept of R square, what did we do there? By taking y equal to constant and by taking y equal to x variables as part of model, you are comparing how much improvement you are seeing in the variance in your y. So that is what we are checking. Suppose if there is no improvement in the variance, there is no impact of your x variables. So that means before and after, can you say that by including x and by without including x, if there is no significant difference in terms of your variance, that means the model is not possible. So this is the place we use ANOVA to compare before and after. That is same as what? If a model is not possible, what does that mean? Here also we'll perform your null hypothesis. What is null hypothesis? Null hypothesis is beta 1 equal to, beta 2 equal to, beta 3 equal to, and so on, beta n equal to 0. What is alternate hypothesis? At least one beta is different from 0. Why? Because if at least one variable is showing some kind of significant impact, that means that before and after there is an improvement. Yes or no? Yeah, impact of X on Y, right? So that is what we need to look at. So this is the second important thing you will look at. So basically, whenever I'm looking at the output, I need to look at all these four outputs we need to look at. Okay, so now let's see how these concepts I'm explaining over here. Suppose now if you look at here, the first table, in this case, if you look at what is your dependent variable, what is your model, what is your method, of course the remaining is related to date, time, etc. And now you can see R square, and of course I will tell you what do you mean adjusted R square in a while. And you can see that F statistics. What is this F statistics? The ANOVA test which I was referring that. So in this case, corresponding F statistics, this is the p-value. What is the p-value in this case? The p-value is almost close to 0, right? Because it's a exponential of minus 14, that is nothing but 0.000 and so on. So that is nothing but if p-value is close to 0, you can reject null hypothesis. What is your null hypothesis in this case? This one. So what is, you can accept alternate hypothesis. What is your alternate hypothesis? So at least one beta is coming significant. So that means the model is possible. So that is what the first information you are getting here.
Chandra, can you please explain once again? I didn't get.
So what I am saying is whether model is possible or not.
Correct, correct. Yeah.
So whether model is possible or not, suppose all betas are close to 0. What does that mean?
It will be null hypothesis.
I mean, null hypothesis, that is nothing but what? Model is not possible.
Correct.
If one of the beta, that means one of the variable is coming significant, that means that some improvement in your error.
Correct.
So that is what we are testing with the help of ANOVA. Suppose if I want to check my null hypothesis or alternate hypothesis, which one to reject or which one to accept it. So that's the place you have this F value, and a corresponding F value, you want the P value. If P value is low, can I reject my null hypothesis?
Correct. Okay, got it.
So that is what I'm rejecting my null hypothesis. That is nothing but what? Accepting alternate hypothesis.
Yes, the model is possible.
That means model is possible.
Okay, okay.
That
Fine.
means that at least one of the beta coefficient is different from 0. That means at least one variable is contributing significant impact on your Y. Now
Okay.
tell me, okay, how you know that at least one variable is coming significant. Now, which of those variables are significant? This is the next step we need to look at. Now let's look at. So this is the place you can see the second table. What is the second table? You can see that each variable, okay, this is my constant. Intercept is nothing but constant. And this is the variable and corresponding coefficient. What is the coefficient means? The beta. So this is the beta 1, this is a beta 2, this is a beta 3, this is a beta 4, etc. That means that corresponding price in 1000, what is my coefficient? Corresponding 4-year resale value, what is my coefficient? Correct? Yes or no? Obviously, because beta 1, beta 2, beta 3, all of them are different, right? So these are my beta 1, beta 2, beta 3, beta n. Okay, now you got the coefficient. Now, corresponding each coefficient, you also have a p-value. This is my, okay, price in 1000 is my p-value is what? 0.002. That means that what? Is it less than 0.05? Then by looking at the p-value, can I say that this is significant or insignificant? This is significant because it's less than 0.05. That means you can reject your null hypothesis. What is null hypothesis? beta equal to 0. Alternative hypothesis is what? Beta is different from 0. So beta is different from 0. What does that mean? It's a significant. So that is what you can see that. Okay, Fourier resale value, can you see that any significance in this case? No, right? So that is what you can say that. So by looking at the p-value, now I can easily identify which variable is significant, which variable is not coming significant. Do you agree with me? Now how this p-value calculated? Based on the t-value. Because you remember in the hypothesis testing, based on the t-value only you will get the p-value. But what is the t-value? The t-value is the coefficient you are comparing with the 0. That means your coefficient comparing with 0. So beta is comparing with 0. That means that my hypothetical, it's one sample t-test if I use it. What is that means? Beta minus 0 by standard error. This is my t-value. Okay, now if you look at what is my beta, this is my beta minus 0. That means that this by this will be my t-value. So maybe you can see that equal to minus, what is that? 0.0483 by what is your standard error? 0.015 minus 3.22. So minus 3.22, of course, this is the minus 3.22. Of course, here what happened is you rounded off with the 3 things. If you do that one, you will get the exact t-value. So now t-value, based on the t-value, you got the p-value. If the p-value is low, then you can say that it's significant. So that's how this particular table is interrelated.
Chandra, can you please show the t-value calculation again? I mean, how did
The t is very simple. What I'm saying is the coefficient, that is nothing but beta minus 0 by standard error.
Why 0? Chandra,
Because you're comparing with the beta is close to 0 or not. Because the your hypothetical value is 0 here.
Okay, got it. Thank you.
Does that make sense? So now you understand how to identify variables are important or significant or not. Okay. Now I think this is clear now. Now what is your fourth one? How good is your model? How good is your model? Of course, by looking at the R square. Can I say that my model is good or not? By looking at the R square, you can say that. Okay, of course, this one in this case around close to 60%. So this is okay, not bad. At the same time, not great also. Of course, this can be further improved with the help of the transformations. Of course, here I did not take all the variables, right? I picked up only few variables. And if I include all the variables, probably that might further improve.
Dropping of dummy variables would improve the R square.
That is, see, in this case, just I shown you for what? I shown you for just for explaining the linear regression. Now, how to, first of all, you need to make sure that there are 2 things you need to make sure that whatever the variables you included, all the variables should be significant. That is the first thing you need to do. That means if some variables are insignificant, you need to drop them first. And if you want to include some more variables, you can include some more variables. That is second thing. And the third thing is, you can include the, for example, instead of price in 1000, what I mentioned, price in 1000, what you can mention, log of price in 1000 can be a better fit.
Okay.
So that time what you can do is, of course, price in 1000 here, price in 1000 is 56% correlation. This is 60% correlation. So that means that price in 1000, if I take a log transformation, the log of price in 1000, you can include instead of price in 1000 in your model. So that way you can improve some more accuracy. Are you able to follow me? So these are the 3 aspects which you need to do that. So now you are clear with the understanding of my model. What is the output of my model? Okay, now how to improve the accuracy and what are the steps you need to follow? Okay, let's understand that. The steps. The first thing you need to make sure that all the variables should be significant in the model. that means that the p-value should be less than 0.05, or sometimes you can relax the condition, probably 0.1, 90% confidence intervals. If I take 95% confidence interval, p-value should be less than 0.05. That is the first thing. The second thing is you should not have any multicollinearity. That is the second thing. I will tell you what does that mean. The third thing is basically what I mentioned, include a transformed variables based on the linearity assumption. Correct? This is my third thing. What is my fourth thing? Add more variables if you have it, so that you can also identify that. So this is the typical things which you need to look at. I mean, to improve further accuracy or making sure that your final model. Are you clear? Okay. Now, I was referring that since multivariate analysis, so whenever I'm referring to the multivariate analytics, multivariate model. So when it's a multivariate model, what does that mean? You including more x variables, more than one x variable, you are calling as a multivariate model. So simple regression is nothing but what? Having a one x variable. Multivariate regression having more than one x variable. Is it clear now? Okay, now if you have a multivariate model, there is some kind of interactions. What do you mean interactions? One variable affects on other variable. Okay, so price is there and you also have resale value. If they are two related each other, one will impact on the other. How it will impact? So that is what exactly we need to understand. This is the place the concept of multicollinearity comes into picture. So what is multicollinearity? Within x variables, one x variable expressed as a other x variables. So that means that one variable depending on the other variables. So suppose I was referring that x1, x2, x3, x4, suppose four variables you have. Suppose if I'm able to identify the relationship between x1 and other x2, x3, x variables. So that means if I'm able to write x1 is expressed as a function of x2 comma x3 comma x4. x2 is a function of x1 comma x3 comma x4. x3 is function of are able to follow me? So what I'm saying is, if you are able to express x1 with other x variables, this is what we call as a multicollinearity. Now, why do we need to worry about multicollinearity? Okay, so let's take an example. Suppose you have a three variables, x1, x2, and x3. So my relationship is something like this. So y equal to 3 times of x1 plus 2 times of x2 plus 3.5 times of x3 plus 100. This is the model, you got it, with the including all three variables, including all three variables. This model is basically, by including all three variables means we did not check any multicollinearity. we did not check any multicollinearity exists or not. Correct? Suppose in this case, what does this mean? All three variables are having a positive relationship. What is the interpretation of this model? Interpretation is what? For all the variables are having a positive relationship with y, and all the variables are significant. And one more thing, assuming that x1, x2, x3 all are in same scale, that means I can compare the betas. If all the variables are in same scale, I can compare the betas. So in this case, if I compare the betas, which one is most significant, most important? X3 is most important, most significant impact. What is the second most? X1 and X2. Correct? Yes or no? So this is the order of thing which you got it. Okay, now assuming that there is a multicollinearity exists. Okay, we did not check it earlier, but there is a multicollinearity exists. So multicollinearity exists means what? X1 is expressed as a X2 and X3. So assuming that there is a relationship between X1 and X2. So that means that what? X1 can be expressed as a X2. Correct or not? Now, if I want to express as X1, suppose the relationship is like this. Assuming that when they have a relationship, so this is the relationship it has. Assuming that this is the relationship it has. So if I have this relationship, now if I include this in a relationship is over here, what is my model equation will be? Y equal to 3 times of 0.7 times of x2, that is minus 2.1 times of x2, plus 2 times of x2, that is nothing but minus 0.1 times of x2, plus 3.5 times of x3, plus 100. So that means that if I include only x2 and x3 variables, this is my equation will be. Suppose if I include only two variables, if I include only x2 and x3 variables part of the model, this is my equation. Suppose if I include x1, only x1 and x3, what is my equation will be? Instead of x2, what we will do? So minus 0.7, so 1 by minus 0.7. 1 by minus 0.7 is nothing but what? Minus 1 by 0.7. What does this mean? Minus 1.42. So that means that your equation will be what? Y equal to what is the initial 3 times of x1 plus 2 times of minus 1.42 minus 1.43, I'm just keeping as a rounding off, times of x1 plus 3.5 times of x3 plus constant. Constant is nothing but 100. So that means that what is your equation will be? 3x1 is subtracting 2.86. That is nothing but what? 0.14 times of x1 plus 3.5 times of x3 plus constant, nothing but 100. Suppose if I include this one, this is my variable will be. This is my equation will be. So basically what indirectly I'm saying is, suppose if I include x2 and x3, this is my equation. If I look at this one, what is the relationship of your x2 with your y? Negative relationship, right? and the negative relationship, is it close to significant? So assuming that the variables are in same scale, that means that this variable is not that much significant, because when earlier the significance you got is how much? With x2 is x2 is you got is 2 times of x2, right? In your original equation, what is that? 2 times of x2. And here what you got? Minus 0.1 times of x2. Here you have a positive relationship. Here you have a negative relationship. How the negative relationship becomes positive relationship? Because you included a multicollinearity variable, which is x1 in the model. Is that clear or not? What I'm trying to say. So indirectly, what I'm saying is, if I don't check my multicollinearity, this is my relationship. But if I include only these two variables, what happened? My relationship is completely different relationship. So here I have a negative relationship, but the negative relationship becomes positive relationship because the variable is correlated with your y, which is influencing on your x. So basically, indirectly what I'm saying is, by including multicollinearity variables, cause the below things. So what is that? Your important variable become unimportant. That's nothing but significant variable become insignificant. Same as significant variables becomes insignificant, or vice versa. Or the other one is positive relationship variables becomes negative, and vice versa. So what happened in this case? It has a negative relationship. By including the multicollinearity variable, it is becoming positive relationship. And the accuracy over here and the accuracy over here will be the same, right? Because the prediction value will not change. Do you think the prediction value is changing here from here to here? If your predicted value over here and here is exactly the same, correct or not? Why? What happened?
Then how multicollinearity will affect it?
That's what I'm saying, that if predicted values are same, but the problem of what it happened is you included some multicollinearity variable, and the interpretation is completely changing over here. What is the interpretation? Here you are saying that if x2 is increasing, by increasing the x2, your y is increasing. That is the interpretation you do that. But what is the interpretation over here? x2 is increasing, your y is decreasing. That means the complete different interpretation you got it. And one more thing, and here you have this variable is almost insignificant, but you are showing as a significant variable over here, right? So when we are taking the business decision, what we will do, we will take that, we need to take some kind of understanding. For example, if you are saying that it's a x2 is increasing and your y is increasing, then what you do, you will spend more money on the x2. Suppose a simple example is marketing spend. The marketing spend can be a multiple marketing spends you do. For example, TV spend, radio spend, news spend, etc. For example, news spend is giving a negative impact, for example, by some reason. What happened? If you are increasing the newspaper spend, you will get low sales. Is it a good interpretation? No, right? So that means that completely you are misguiding the business. And one more important, since this variable is impacting, insignificant variable become significant, significant variable become insignificant. That kind of situation, what happened? You will drop insignificant variables. So that's also create a problem, right? So that's the reason multicollinearity is extremely important to, to handle that. So that is the one reason when we are looking at the output basically you cannot drop all the variables in a single go. Suppose if you look at here, these are the list of variables are not coming significant. Correct or not? But you cannot drop all the variables in one go. Why? Because of multicollinearity, some variables become insignificant. Either you need to check multicollinearity first, or you need to drop one by one variable. So for example, in this case, what is the variable which you can drop? So for example, if this is the equation, right? So what you can drop is, of course, you can use dot fit here itself. And of course, what you want to do is, and summary of L1. Okay. Suppose now which variable you want to drop it? Maybe whichever is highest insignificant. For example, in this case, the cup weight is most insignificant thing. So you can drop that. So probably you can drop this variable. Now you look at the output of this. So now you can see that the variables are still insignificant. So the next insignificant variable is what? Width. So you can drop width variable. And now you can see that what? Still there are some insignificant variable. What is the next insignificant variable? Probably fuel capacity. So fuel capacity, you can drop it. Now what is the variables which are coming insignificant? Probably you can see that length also, is not important. So probably you can drop length also. So in this case, if you can see here, and what is the variable is insignificant? Horsepower. So probably you can drop horsepower. And you can still see that, of course, still there are some variables are insignificant. Which one is insignificant? Fourier resale value.
Chandra?
Yes.
But the more we are dropping the insignificant variables, the R square is getting lowered, right?
Of course, the R square is lowered, but dropping insignificant variables is important because we will discuss about there are consequences of having a more number of variables. Okay, but at this point of time, if there is a variable is insignificant, there is no point of keeping that variable. So now if you look at these variables are coming significant, now if you can figure all of these variables are almost less than 0.05, can I say that these variables are significant? This is how you need to look at. Now you can see that the R square earlier was how much?
Approximately
0.59.
Yeah.
And now what is 0.57? Of course, a 2% drop is there. But at the same time, you can see that the adjusted R square. Earlier it was 0.55. Maybe you can see that. I will discuss about what is adjusted R square in a while. But if you see that earlier it is earlier also 0.547, and now you can see that 549. It's increased. I will tell you what is that reason. But at this point of time, now you understand how to drop the variables. You cannot drop all the variables in a one single go. Why? Why you can't drop? Because sometimes the insignificant variables become significant variable insignificant because of the multicollinearity. Right? So that is the first thing you need to do it. Once you are sure with this one, okay, these are the list of variables which I want to use it. Now what is your mathematical equation will be? Okay, so my intercept is 2.5129 and 0.0558 is my price in 1000. And like this you can create my final equation like this. And once I have my final equation, what is your actual variable? Sales in 1000, right? So predicted sales in 1000 and is nothing but exponential of log sales in thousands. Okay, predicted. This is my equation or not? Because once you know the betas and constant, what is your equation? Because earlier it was log sales in 1000, right? but my actual value is not log sales in 1000. In my business perspective, I need to predict what? Sales in 1000. So taking the exponential, you are transforming back. So that is what exactly we are doing here. Does that make sense or not? So is it everyone clear with what is the interpretation of the model, what is your final equation, and what is your final predicted value? You can use it.
So we have removed these variables after we got the model and we got the p-value. Like before building the model itself, is there a way to remove?
We will discuss about that. There is a way.
Part that equation you have given?
So the equation is nothing but what? Your equation is basically what? Y equal to beta 1 x1 plus beta 2 x2 plus beta 3 x3, right? So what is your hypothetical relationship? The hypothetical relationship is this one. So now what is your beta 1? What is your x1? X1 is price in 1000 and the corresponding beta. And beta 2 into, of course, 4-year resale value is not there. So what is your second variable? Engine size. Engine size is multiplied with 0.3565. Or a wheelbase multiplied with 0.0426. Or fuel efficiency multiplied with 0.1010. And this one multiplied with this one. So that
How
is
do we determine? How do we determine the accuracy of the model?
So that is yet to reach, because one is, I told you, the R square can be, one of the metric, but there are other metrics which we'll discuss about that.
Okay.
So now you're clear with this? Okay. So there is a one interesting aspect which I want to discuss. So we mentioned that if one variable is expressing as other variables, I'm calling it as a multicollinear. Suppose if I take x1 is your dependent variable, the remaining x variables are independent variable. I can also establish some kind of a linear regression over here to establish a relationship. So if I do that, I can also get R square. Okay, for example, I got 0.3, 0.7, 0.2, 0.6, suppose. And in this case, R square is high. What can you say? That the relationship is strong, and that means that this one is strong relationship. That means x2 is expressed as x1, x3, x4, and x4 is expressed as x1, x2, x3. So that those two are highly correlated. That means that one variable is expressed as other variables. So most probably x2 and x4 are interrelated. That's the reason you got this kind of a high values over here. Okay, now R square is high. So if I take 1 by 1 minus of R square. So what does that mean? 1 by 1 minus of, sorry. What is this? If my R square is high, can I say that 1 by 1 minus R square is high? Maybe you can see that this one and this one, you can see that the values are high. So this is what we called as a VAF. That's also called as a variance inflation factor. So the VAF is high. Can I say that my model having a multicollinearity? So what is the cutoff is? Generally the cutoff is greater than 2. If the data have any variable with more than 2, that means that they have a high multicollinearity. So that you need to look at each individual variable wise. Okay, so we will see that how that can be helpful. Of course, this VAF value checking also is one of the way to reduce the variables. Because if two variables are multicollinear, then only you will have a high VAF value. If you drop one of them, you can automatically dropping one of the variable. Like if two variables are correlated, then only you will have high VAF. You need to drop one of the variable. So that's what exactly, which we generally if high VAF value is there. Suppose this is the high VAF compared to this one. So obviously x2 is expressing better in terms of x1, x3, x4. So probably you can use x2, you can drop it, and the remaining x1, x3, x4 you can include it. Make sense? So now you are clear what is a VAF and how VAF help you to reduce the multicollinearity.
So this VIF we can know once we know the functions between those variables, but how do we get those functions within X2?
Within the x variables, so I'm saying that this is explaining the concept, but generally what happened is there is a function we have in Python that automatically calculate in the back end how the relationship and get me the final VAF values. So I will show you that how to do that. But concept of VAF, what does that mean? One variable you are expressing with other variables and you are looking at the R square corresponding that relationship. And the R square is high, your VAF is high. If VAF is high, you can say that the multicollinearity exists. How much VAF? What is the cutoff? It's a point, 2 is the cutoff. But sometimes, some company, sometimes some people will do even cutoff is a 5 also people will take. But don't get confused around that. So a typical cutoff generally will take is 2. But if you want to relax it, you can take till 5.
Yeah, Chandra, just one doubt.
Yeah.
We mean to say when R square is high, we will conclude that VAF is high, and that means the multicollinearity exists, right?
Correct.
Whether if it is existing, that would that be any effect? What is the effect on the model? Is it like good for the model, or like how is it?
So that is what I was explaining earlier, right?
Correct. Yeah.
So multicollinearity exists means that creates some kind of a problem in your model. What is the problem? You will get it. Some important variable becomes unimportant. Some positive correlated variables you are showing as a negative correlation, or vice versa.
Oh,
So
okay.
which variable do we decide to drop? Can
So
you
which
go up
variable
again?
to decide the drop is something which we generally do. Suppose high VAF is there, then you will drop that variable.
No, so go up, for example, you calculated those VIF like 0.7. So does that mean we drop X2?
Yes, exactly.
This case?
Exactly.
Okay.
So this is ideally you should drop x2, but some reason x2 and x4, you need to decide which one to drop. And suppose x4 is having a lot of missing values, you imputed with some value. Then I will drop x4 rather than x2. Able to follow me? That is a one kind of scenario. And the second scenario is sometimes the business interpretation they are much easier in x2 compared to x4, then probably we will drop x4. So business interpretation, business implementation. For example, there are two variables. You have a price variable and you have some other variable for 4-year resale value. 4-year resale value is really you will able to understand for a business perspective, because the resale value can varies depends on the different parameters. So compared to resale value is not in your control, but price in 1000 is in your control. So probably business perspective, probably I will use price in 1000 compared to resale value. So that time I will drop resale value. Does that make sense? So sometimes business also, interpretation also will make sense whether to drop or not. And the second way is, by looking at the high VAF values there, you will drop that variable.
So, Chandra,
Yeah.
if we can determine based on R square only what is the need of VIF then, because if R square is high, we can say that we can drop that variable.
So
Because
guys, one important thing is R square is, what happened is a lot of times people will get confused with R square at a variable level, R square at a overall level. So that's the reason the VAF is much easier, because to get the cutoff perspective. So as I said that R square, if you know individual variable wise R square, individual variable wise VAF, both are same. Both are talking about the same thing. So, more appropriately you can look at is VAF is, because it's easy to understand. Because otherwise you will get confused with overall R square.
Okay.
Because you also have overall R square, right?
Yeah.
Chandra, another question. So somebody else also asked over here that if we do a transformation on any of the x variable, and we get the equation, then we need to transform them back before the before deciding the prediction.
No, for x variables, you don't need to, do that. Only for a y variable, you need to do, because y variable is you are predicting a value.
Okay.
Correct.
Okay.
When you are predicting value, you cannot give the value of sales in 1,000 in log scale, right?
Yes.
But you can include your x variables with as it is transformation. There is no issue. But only thing is, when you're implementing it, you should have a log of x instead of x. In case if you are using a log transformation.
Okay. 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 Got it.
Does that make sense? Okay.
Yes.
So now you understand the concept of the VAF and how VAF help you to reduce the multicollinearity. Okay. Now there is a one important aspect which I did not talk about, the difference between R square versus adjusted R square. Okay, so when I'm defining the R square, what did I do? What did I do?
With respect to x.
R square is, 1 minus. So for example, first I calculate the percentage of variance explained by this one. How did you calculate the percent? Okay, so with constant, so that means y equal to c, what is your error? That is what we call it as a sum of squares of deviations, SSD. And with x variables, what is your error? SSE. And your R square is nothing but SSD minus SSE divided by SSD. That is same as a 1 minus SSE by SSD. This is my R square, right? So actually, if I look at sum of squares of deviations and sum of squares of error, there is no issue. If I include, suppose if I have n variables, if I take the average contribution of variable in terms of the explaining error, if I want to know, suppose if I use 10 variables, how my average sum of squares of error is contributed. Suppose if I want to know, that is something which I can't do with the R square. Okay, anyway, so for the time being, what you have is R square is nothing but 1 minus sum of squares of error by sum of squares of deviation. Okay, so now this is R square, you got as a 50%. This is 50%. So assuming that you are including 3 variables or maybe 4 variables. If I include only one variable, my R square is 22%. By including x2, I got as a 48%. By including x3, 50%. Or maybe a 49.9%. But including x4, 50%. Okay. And by including x5, that means that x1 here, this is x1 comma x2, this is what my R square. x1, x2, x3, this is my R square. And x1, x2, x3, and x4, this is my R square. x1, x2, x3, x4, and x5. My R square is 50.01%. So what happened in this case? By increasing the variables, you seeing that the improvement in R square. But if you look at look at these 3 things, what is the improvement you got it? Almost you got 22% to 50% close to. But by including x4 variable, do you see any significant improvement? It's almost nil, right? A 0.1% or something. By including x5 variables, do you see any kind of improvement? it is a just 0.01% improvement. So what indirectly I'm saying is, by including more variables, do you see there is a significant improvement in your R square? So actually, if you look at this one, adding X4 and X5 variables is not contributing much to your model. Okay, that is the first point you should keep in mind. Now, by adding more variables, what is the problem? Is there any problem? Of course, there is a problem. What is the problem is the model complexity increases. So if you have one dimension, if you have two dimension, if you have three dimension, if you have n dimension, the complexity of the model increases because the error, so the model complexity increases, and that will create a problem of overfitting. What do you mean overfitting? What do you mean overfitting? Any idea? The overfitting is that training accuracy is greater than and testing accuracy. So what does that mean? The training accuracy is high and testing accuracy is low. Suppose if I look at accuracy on the training data, suppose you got 60% and accuracy on the, train data, for example, 50%, 50.01%. This is what you got by including 5 variables. The testing data, probably you might get 35%. So this is, I'm saying that if the train data you are getting 50% accuracy and the test data you are getting 35% accuracy, can you say that that model is validating on the new data? Right? So if the model is not validating on the new data, can we rely on that model? Is the model stable? No. So that means you cannot really implement that model on the new data because you are not getting a similar accuracies. That means you are not confident on the model. So that means that this is the problem we call it as a overfitting problem. So the overfitting is nothing but if the model is working on the train data but not working on the test data. That means not working on the new data. So this is the problem you will get it due to multiple reasons. Okay, the overfitting problem, you may get it with the multiple reasons. One reason could be low amount of data. That means number of observations are low. This can be one possible reason. The other possible reason is having more variables. That means some unnecessary variables included in the model. This can be one reason. Or having more transformations in the data. So that means you include a lot of transformations, but the transformation is not contributing a significant impact, and that's also can cause an issue, right? So these can be a possible reasons, right? So to avoid that one, this is the one of the key thing. Of course, if you have low amount of data, obviously probably you can increase amount of data by adding more number of observations, and having a more transformation that is in your control. When you are looking at the y and x, if you see that x variable, by improving the linearity relationship, you are adding some more variables, but by adding that transformation, if you don't see too much significance, you don't need to include that transformation. Okay, so these could be a possible reasons. So this is the one of the biggest problem you will face. What is the problem? Your model works on the training data. You will get a very good accuracy on the training data, but on the testing data, you will not get it. Right? So this is what we call it as a overfitting problem. There is another problem called underfitting problem. What do you mean underfitting? So of course, both train data and test data, train and test, the accuracy is low. So suppose like 50% accuracy, it's not that much. So you're supposed to get 80% with the data, but you got only 50% accuracy. So this can be one reason is you are not having, this is the problem of underfitting. So not having right variables or not many variables or not chosen right variables and right transformation, or created a bias in the data by by data preparation. So like you included a lot of observations which is missing with the mean or something, which create a lot of bias in the data. Or some reason could be not using right technique. So the technique can be, what happened is, linear regression may not be a good fit in this case. There might be some other technique can be a good fit for this data. Right? So like this, there are n number of reasons can be for an underfitting problem. So basically, overfitting and underfitting both are important to handle. More important is overfitting problem. The reason is, if the data is working, if you are getting a very good accuracy on the trained data, but you are not getting good accuracy on the test data, how will you be confident on the model? Right? You cannot be confident on the model. That means that model not going to work on the new data. So that is the reason, you need to take care of this overfitting, the overfitting kind of scenario. So you need to reduce the variables which are unnecessary. So that's the reason, first of all, you need to look at which variables are not contributing. So this is, by looking at these variables, so the adjusted R square, I will tell you. What the adjusted R square is? 1 minus SSE by N. N is nothing but sum of squares of error, that is average of errors by SSD. 1 second, I think something is missing. It's basically the R square and number of observations, number of variables you are included. So what does that mean? R square is number of variables included. If the variables are included, but if it is not contributing much, that means you are adding some penalty to that model. You understand what I'm saying? So what I'm saying is, R square is high. So by adding one more variable, if you are adding a good amount of error, the R square, then the variable is good. If the good amount of thing is not adding, that means that you are adding some penalty to that. By adding one more variable, you are reducing the accuracy. So that is what the adjusted R square. So generally the adjusted R square will be lower than R square. Okay, adjusted R square will be lower than R square. So, and if the difference between the R square and the adjusted R square is high, what does that mean? There are some unnecessary variables are present in your model. So what you need to do, if the difference is a significant, generally plus or minus 2, right? That means that there are some variables which are not contributing to your model. So then that means you need to look at back and see which variables are unimportant. Is this clear now? So now you understand why I am referring to that adjusted R square and what is the reason why we are dropping the variables. Less than 2. That is what I was referring to. That is the best practice. But again, as I said, that these are all our best practices. You cannot have too much difference between your R square and the adjusted R square. Suppose if you see that earlier, what is the difference you see here? The difference is almost 5, right? But if you see the difference here, almost 2, 57 and 55. Correct or not? So that is what we need to target. Does this make sense, guys? Okay, so So Ritesh, I was already mentioned this answer to you. I mean, the X variables, you don't need to transform back. Only Y variable we need to transform back. Okay, so once you got the model, what is the next thing I need to do? Okay, so check on the test data. So for that, what we need to do is, okay, so you got the model. Okay, assuming that this is my model, I got it. Now I need to calculate the matrix. Okay, for that, what I will do is, okay, this is my all the variables. So what I need to do is, I can, okay, 1 second. I already have all these. Okay, so now what we need to do is, you need to calculate your train and test predicted values, right? How will you get the predicted values, guys? So what I'm doing is, my LM is my model, and LM.predict, I can get the train data and test data, my predicted log sales. Okay, so let me show you that. You remember we discussed about, so LM is my model, dot predict, and what is this? And you need to specify train data, then what you will get it? This is what? My predicted value. This is a predicted value of what? Log sales, right? So this is what exactly I'm calculating. So I'm creating a new variable in my train data, lm.predict train. So that is nothing but predicted values of train data and the predicted values of test data. And now I need to calculate my actual sales and my predicted sales in a normal actual sales and predicted sales. You have in both in log format, right? It's the log transformation. So now I want to go back. So I applied on the exponential transformation. So then you got the finally the train and test. So this is what you got it. So now suppose if I look at the train data, so now you can see that all my variables, and this is my log sales in 1000, that is my original log variable, and actual sales is, that is a original sales in thousands, and the predicted sales and the predicted log sales, predicted sales. You got it now? Yes or no? Okay, now once I have this one, I need to calculate the metrics. What is the metrics I can calculate? Like RMSE. What is RMSE? Suppose my actual value is something like this. Let me show you that. Suppose you have your this is your data and this is your Y value, right? So let me show you this. Okay, this is your predicted value. Okay, predicted sales, and this is my actual sales. Now RMSE means the mean squared error. I mean, of course, MSE squared error. Squared error is nothing but what? this minus this, actual minus predicted, and square. So this is my square of error, and taking the average of this one, what? This is nothing but what? There is a mean squared error. This is MSE. RMSE is nothing but what? Root mean squared error. This is a root mean squared error. So this is what RMSE. Okay. Now what is a MAPE? MAPE is nothing but percentage error, absolute percentage error. What does that mean? Absolute value of this minus this by actual. This is what my absolute percentage error. And taking the average of this. This is what we call it as a MAPE, mean absolute percentage error. Correct? So now you have the actual and predicted. I can calculate RMSE, I can calculate MAPE, and I can also calculate the correlation between actual and predicted. How can we do that? So correlation, this is my actual, comma, this is my predicted. Of course. So you got the high correlation. Okay, so like this, you can also calculate all of these things over here also. How can we calculate? So this is what I have done it. My actual is this one, and my predicted is this one by actual. This will give me what? Percentage error, right? So this is absolute percentage error, because since it's vector, A vector, B vector, A minus B, you will look at the position wise difference and position wise percentage. Correct or not? So then taking the average of that, that will give me what? Mean absolute percentage error. That is what we call as a MAPE. And calculate the MAPE for trained data, and RMSE for trained data, and correlation for trained data, and similarly for test data, test data, test data. So this is what I'm looking at. So now you can see that these are my train related metrics, and these are my test related metrics. Now you can see that this is my MAPE for train data, MAPE for test data, and this is for RMSE, this is for RMSE, and here the 61 correlation, here is 34% correlation. Of course, in this case, by looking at the metrics, obviously it is not a, it's not good model. I'm not saying good model or bad model. It's not validating on your test data. Right? So are you clear on that? How to verify your model is working on a trained data or a test data? You know, both the data set, you should get a similar kind of results. So the reason why you did not get is, it could be any reason. This is what we call as a overfitting problem. So in this case, this model is overfit or not? Is the model overfitting or not? If S, you need to relook it. So I told you what is the possible reasons for overfitting the model. It could be any reasons, right? I already told you. So it could be any reasons. I already mentioned that these can be some reasons. So low amount of data, or having more variables, or having more transformation in the data. It can be any reasons, right? So that means that, of course, this is etc., because I cannot say that these are the only reasons. Of course, these are the very popular reasons. So that means that what you need to do, you need to relocate the model. Right?
SPSS, we used to have an auto classification which used to come up with the best models. In Python, we have something.
There is no automated process, but yes, we can automate it. Okay, but at least at this point of time, you conceptually, you understand whether your model is making sense or not. That is the first thing. And second thing is, once you get the model, your model is working on that new data or not. And the third thing is, what could be the possible reasons for not getting the model? These are the three things you need to look at. Now, okay, one possible reason for the overfitting is multicollinearity also. So, one possible reason having multicollinearity. There could be some reasons for this also. So now, how to check multicollinearity? So I told you earlier multicollinearity. How did we do that? I told you VAF can be one of the thing, right? So I told you. So how to check that multicollinearity part? I will let you know about that. So check the multicollinearity in your final model. So how to check it? So this is the place we have in the stats models. There is a function called variance inflation. So there is a module called variance inflation factor. So this is the module. Under that module, you have a variance inflation factor module, and using this module, and you can calculate the VAF value. So let me show you that. So for example, what is your final equation? What is your final equation? For example, your equation is something like this. This is your equation, right? So now you need to look at this equation is something like this. So basically, first you need to extract your y and x using the D matrices function. And once you have y and x, the variance inflation factor for each variable, and you are, this is basically, that, what is this one? List comprehensions, the looping within the list. So the list comprehension, so for each variable, for I in range of x shape, that is nothing but each variable in your data, you are calculating the VAF value. So that means that once you get the VAF, and the VAF looks like this. So now